Hello everyone and welcome to today's webinar on SPaT Challenge Design Considerations. This is part 2 of our SPaT Challenge webinar series, where in part 1 we had a webinar to learn about the SPaT Challenge activities, workshop series and other resources. You can view the webinar recording and the slides for the part 1 on our website. Today we will be covering topics on SPaT messages, V2I and the agency experience with deploying onboard units. The next part of our SPaT Challenge webinar series will focus on map messages, vehicle position correction, and DSRC licensing. This upcoming webinar is scheduled to occur on April 17th, so we encourage all of you to register for that webinar also. If you don't know already, the National Operations Center of Excellence, NOCO, is designed to offer resources and support the TSMO transportation systems management and operations community. Feel free to browse the entire collection of resources in our Knowledge Center and subscribe on our website to get our newsletters and major TSMO announcements. The links are shared with you here in the useful links box on the right side of the screen. For this and every webinar, a recorded version of the webinar along with the slides will be sent to you in a post-webinar email within 1 to 2 days. The recorded video will also be available through the on-demand learning section of the website. We will have a question and answer session at the end of the webinar. So if you have any questions, we encourage you to enter them in the question pod at any time. The questions will be read out loud one at a time, and our presenters will answer each question. Now I want to quickly go over today's agenda and the presenters. The bios for the presenters are available on the webinar webpage, so please refer to those to learn more about our speakers today. First, we have Blaine from Utah DOT, who will go over an introduction in the beginning. And next, we will cover the SPaT messages, data assembly, and the signal controller interface by Patrick Chan from Consistech. Our next presenter is Chris Stanley from Leidos, who will cover content on V2IHub. And finally, we will have Faisal Salim from Maricopa County DOT, who will talk about the agency experience with deploying onboard units. So that is all I have, and with that, I would like to hand it over to Blaine to start us off with the webinar. Blaine.
Thank you, Nilo. Appreciate that. It's great to be here with Patrick and Chris and Faisal and to hear about their expertise and have them walk us through some good technical issues that will be very helpful for all of us. So welcome to everyone. We appreciate everyone joining. We've got over 130 people online today, and probably a few more will trickle in. And so it's great to have everybody with us. We're excited about the SPaT Challenge and everyone's interest in the SPaT Challenge, and we hope to provide you with some good detailed information today. I'm sure everybody knows this, but the SPaT Challenge is really a challenge for those of us who are in state and local agencies to deploy DSRC infrastructure to broadcast SPaT and MAP in about 20 intersections in each state by the first part of 2020. And the map that's here, you can see the agencies that have accepted the challenge. The blue pins indicate those agencies that have their system running and have completed the challenge to that level. And we're anxious to put more pins on that chart for those of you who are moving forward with this and accepting the challenge. As Nilo said, this today is really the second of our webinar series. Our first webinar was a couple of weeks ago. We talked about some introduction to the SPaT Challenge, talked about the systems engineering approach, and an overview of a model concept of operations. We also discussed corridor selection and procurement issues and costs. And if you weren't able to join that, I would encourage you to go to the Operations Center website, and I'll show you in a minute how to do that, and to review some of those topics. Here is a screenshot of the Operations Center website where the SPaT Challenge is hosted. You can see the web link at the top of this slide, and the arrows point you to the two places where from this front page sheet you can get in to see the webinars. And the recorded webinar is there, as well as the information from the webinar, the slides. So I would encourage you to jump there and get that information if you missed it and if that's some of what you're looking for. Farther down on that page, right below the SPaT Challenge map, you'll see the location where you can link in and provide us with the information on your corridor that you're planning to deploy and that you're working on, so that we can have that information and add it to our list and get a pin for you up on the chart. So we certainly encourage you to do that if you haven't done that already. We talked about the model concept of operations and model requirements at our previous webinar, and on the SPaT Challenges resources page, here's where that document can also be found. So that's been added along with a bunch of other resources that are up on that page. This is the second of 6 webinars, actually. We call this Design Considerations Part 1 today. Design Considerations Part 2, which is actually the 3rd webinar, sorry for that confusion, will be on April 17th and talk about map messages and vehicle position correction and DSRC licensing. Then you can see there will be a webinar dedicated just to the map creator tool that USDOT has developed, another design considerations webinar, and then finally a webinar on deployment and validation of the messages you're being sent. So I would encourage you to sign up for those additional webinars. Wanted to make sure you knew that those were coming, and those can also be found on the resources page where the recording from the first webinar is found. So with that introduction, let me again welcome everybody here and turn the time over to Patrick Chen to talk to us about signal controller interfaces for SPaT messages. Patrick.
Great. Thank you, Blaine. So for the next couple of slides, I'm going to be presenting information about the SPaT data that grows across the interfaces at a signalized intersection. So my presentation is broken up into 3 parts. We'll first start by reviewing the actual SPaT message to try and better understand what intersection information, what signal information we can provide to travelers, whether it's a driver or a pedestrian. Then we'll review the proposed NCCIP 1202 version 3, which should be in ballot any day now, but look specifically at that standard to see how it specifically proposes to support the connected vehicle environment and SPaT information. Then we'll finally end by taking a look at some current implementations that broadcast the SPaT messages and what data they provide and how they provide it. We'll first start by looking at signalized intersections. So in the connected vehicle environment, we normally consider the following components at a signalized intersection. In the middle, we have the signal controller unit. On the right, we have a traffic management center to monitor and to control those signalized intersections. And on the left, we have a roadside unit that's sending information or exchanging information with connected devices, which may be a vehicle or maybe an application on a smartphone by a pedestrian. So when we talk about ITS standards, we're actually talking about the standards that define how the data exchange between one or more of these components and the vocabulary used to provide that data. So we'll first start off by just looking on the left by reviewing the SPaT message itself. When we talk about the SPaT message, we're really specifically talking about the interface between the roadside unit and the connected devices themselves. So the SPaT message is actually defined by the standard SAE J2735. It was developed with international community input, meaning that, for example, in Europe, they actually use the SPaT messages also to provide signal timing information. SPaT, in case you're not familiar with it, actually does stand for signal phase and timing message. So over the next couple of slides, we'll just skim through most, but not all, the information that can be provided in a SPaT message. In the interest of time, we'll only talk about those key pieces of information that agencies may be interested in providing. in the SPaT message. So each of the following tables that we're going to show describe the information that are in the SPaT message. The last column actually indicates whether that information is required or is optional for when we broadcast SPaT message. The header in the information above the table, in this case message MSG underscore signal phase and timing, is a reference, so you can, if you're looking for more information, this is where you can find it inside the J2735 standard. So on this page, a single SPaT message can provide intersection status and signal timing information for up to 32 intersections in a single message. So it's not limited to just one intersection. Each SPaT message can optionally contain a timestamp, so this is the time when we sent the data, and a name for the group of intersections that might be included in that message. So for example, we might have the name DuPont Circle, and DuPont Circle may have 3 different intersections, for example. So this message is for the 3 intersections at DuPont Circle. The SPaT message can also contain regional extensions, which is something that we may define for a specific region. Be unique for a region. Remember, the SPaT message is intended to be used internationally. So a region may be Europe, for example. Europe has defined some additional data elements that they want to include in Europe. And in the future, you may want to decide to have some specific data elements for North America, though none exist right now. But in the future, that's something that we may be interested in doing. For each intersection, the SPaT message can contain an ID. It should be a unique ID and consists of 2 parts, a regional ID and an intersection ID. So we've been trying to figure out to design a schema so that we can design a unique ID for every intersection in North America. We haven't quite figured it out yet, but we're trying to work on it. Next is the revision number. So it's kind of like a message counter. The message counter gets updated, incremented every time you send a new message. There's an international standard called ISO TS 19091, and I have the reference at the back of the slides that indicate that message count should only be incremented when the message content changes. So if nothing in the into SPaT message changes, you don't need to increment that message counter, because essentially the vehicle will say, oh, message count hasn't changed, so the information hasn't changed, so I can really ignore the remainder of the message. So that was the intent of the message counter. There's also a status data element, which provides the general status of the intersection. So is it in preempt, for example? Is it operating properly? Is it running traffic fixed time, for example, and failure flash? And then the SPaT message also contains information about the movement, the status of each movement through an intersection. So looking at the intersection, what kind of information might we be interested in about a movement? So for a movement, we want to know, and a movement is a specific maneuver through an intersection. We want to know, are we allowed to move right now? Is it green, for example, or is it permitted, or is it yellow? And we're also interested in when do we expect that movement state to change? So is it in 2 seconds or maybe 15 seconds? So that's information that's included in the SPaT message. And this table just provides a little bit more detail specifically. For signal group, the signal group ID is used to identify each particular movement to an intersection. We also use this signal group ID to link it to a map message. And we'll talk a little bit more about that later. But for the event state or the movement phase state, we want to know, is it a protected movement? Is it yellow? Is it red right now? Is it a flashing yellow, for example? Timing, when do we expect the time that movement to end, whether it's a red, when do we expect the red to end, or the protected green end? Interestingly, we can also provide speed information, advisory speed. So we can say, hey, for this left turn, for example, we advise that the speed be 15 miles per hour. Or we can actually provide specific advisory speeds for a specific type of vehicle. So for general vehicles, it's 25 miles per hour, but for a truck, we may want to say it's only advisable to go 15 miles per hour. This is more information about the time when the event will change. So the only thing that's required is the minimum end time. So what's the earliest time that this movement state will change? It's also possible that that time has already been passed. So we may say, well, it's going to change 3 seconds after midnight, but you might be in 5 seconds after midnight. So that essentially means, oh, well, it could change any split second now because the minimum end time has already passed. So there's other information that we can provide. Start time, when did the state first begin? When's the maximum? So what's the maximum time? The latest time that this state will end. The likely time, when do we think most likely the state will end, along with confidence. How likely do we think that likely time will occur? And next time, which is more for eco driving, for example. Oh, well, it's gonna, when will the green start up again? So for my eco driving algorithms, please note though that these are now timestamps. The earlier versions of the J2735 had time to change, meaning it's going to change, the state is likely going to change in about 3 seconds, and then a tenth of a second later, they might say, oh, it's likely going to change to 2.9 seconds. These are now timestamps. These are the times, the time we expect that that the phase state will end. That way, we don't have to send updates every tenth of a second. We don't have to worry about communications latency. So the earlier versions of the J2735, like the safety pilot, used time to change, and now the current version uses timestamps. Two other pieces of information that might be of interest in the SPaT message are something called enabled lanes and something called maneuver assist. The enabled lanes, for map messages, when we developed the map messages, it was intended that map message will rarely change, meaning the same map message should be applicable for a month, maybe years before it changes again. The only times you change the contents of a map message really are when the roadway geometry physically changes, meaning you add a different lane, or perhaps you do some restriping of the lane at an intersection. So, but there's conditions where a same physical lane, maybe the use might vary by time of day or day of the week. So, for example, during certain times, a physical lane might be a parking lane or for reversible lanes. Maneuver assist helps provide additional dynamic information about a specific movement through the intersection. So now showing a graphic example, we have here a lane 1 and a lane 5. In the map message, physically they're the same lane, but in the map message we may say, hey, when lane 1 is active, it means it's being used as a parking lane. So no vehicles should be driving in lane vehicles using lane 1 because it's a parking lane, while lane 5 is a travel lane. So in the SPaT message, you may say, oh, during most times a day, lane 1 is active, and this will show up in the SPaT lane. So that means use lane 1 when lane 1 is defined as a parking lane. But perhaps during rush hour, we may say, okay, lane 1 is no longer active, lane 5 is now active. So that means, hey, it's no parking. You can use it as a travel lane during rush hour. So that's another use of the SPaT message. And talk about maneuver assist. You see here in lane 23, we may have a left turn allowed that goes to lane 13 or 14. So if I want to make a left turn in lane 23, I'll end up in lane 13 or 14. That's in the map message. But in the SPaT message, we may provide information about that particular movement that says, hey, there's a queue right now for vehicles wanting to make a left turn, which may be, let's say, 100 feet long. Or, oh, we've detected a pedestrian or a bicycle in that crosswalk that conflicts with that left turn movement. So it's a bit that says, hey, be careful. Tells the vehicle, hey, be careful. There might be someone in that that conflicts with your left turn. So that's a second piece of information that can be included in the SPaT message. So what these really demonstrates is that the SPaT message really should be used in conjunction with the map message. The map message defines the lanes and the possible movements at the intersection. It's not expected to change unless the roadway geometry changes. The SPaT messages uses that information from the map to identify the enabled lanes, which lanes should we actually be using right now, and to provide dynamic information for a specific movement. For example, if there's a potential pedestrian or a conflict, and what key information for that movement. And both contain something called a data element called signal group ID. It's through this data element that we link the SPaT messages with the map messages. Next, I'm going to talk a little bit about NCCIP 1202. We've just started working, or actually, we now currently have a version 3 that's hopefully in ballot. What we talked about so far, we focused on the roadside, the interface between the roadside unit and the connected devices. So now we're going to focus on the other two interfaces between the traffic manager center and the signal control unit, and also between the signal control unit and the roadside unit. So if you're not familiar with NCCIP 1202, it's really standard that defines the data that is used between the traffic management center so that we can manage signal controllers, such as monitoring the signal controllers, monitoring status, being able to change timing plans in the signal controller. Version 3 is currently in ballot. And in version 3, we've added some systems engineering content. So instead of just being a data dictionary and with some data objects, it's like, hey, good luck figuring out what these data objects mean. We now added user needs and requirements. So you select the user needs, indicates what requirements might be applicable, and based on those requirements, we indicate what data objects and dialogues can be used to fulfill those requirements. So we also added support for a cabinet, like say, is the cabinet temperature really high, manage inputs-output mappings, exception reporting or traps, and also support it for the connected vehicle environment. So our supported connected vehicle environment consists of the following user needs: being able to configure the interface between the controller and the RSU, meaning what ports are open, what data do we want to share between the signal controller and the roadside unit. To be able to generate and exchange SPaT data, not only provide SPaT data to the roadside unit, but to also monitor what's going out in the SPaT messages at the traffic management center. The third one, being able to generate and exchange map data, was interesting. When we started out working on 1202 version 3, we didn't expect to have this user need, but we quickly realized that we had to make sure that the SPaT data that is being provided matches the map data that's being used. If the SPaT and map data don't match up, we can cause traffic accidents at the intersection. So that's why we added that specific user need. And for the last bullet, one of the interesting benefits of the connected vehicle environment is we have a wealth of data that might be available from these connected vehicles. So we've added we support a user need so that we can get that information from the basic safety message and personal safety message and use it as detector inputs into traffic signal control. I apologize for this graphic a little. This is taken directly out of the NCCIP 1202 version 3. In the left side between the DSRC radio and the CV roadside process, that's actually the SPaT messages that are being broadcasted. What this is really a logical architecture, meaning when we started talking about the connected vehicle interfaces, we realized that there were at least two different processes that we had to consider. One is the ASC process, which is the normal signal timing operations that we associate with a signal controller. But we also added this process called the CV Roadside Process, which is the connected vehicle applications, being able to generate and the SPaT and MAP messages, being able to receive the basic safety messages and the personal safety messages. So, and I'll show why later in the next slide, but we started looking at what data goes between these different processes, these different components. The first one we did was take a look at the traffic management center to the ASC process or the signal controller. So the data that goes back and forth includes managed ASC, meaning the basic monitoring and controlling of the the signal controller, but also being able to get from the signal controller the SPaT information, the SPaT data, so the traffic management center can visualize, see what SPaT data is being generated by the signal controller. We also looked at between the traffic management center and the CV roadside process, the CV application. With that, we wanted to at least be able to manage the connected vehicle detectors, meaning using the basic safety messages as detector inputs. Well, we want to manage those detectors, but also to monitor, hey, what map data is being broadcasted by the CV roadside process. Third, we also looked at the interface between the signal controller and the CV roadside process. So the signal controller has to be able to provide the SPaT data to the CV application, and the CV application has to be able to provide CV detector actuations, the information from the CV detectors back to the signal controller. The reason why we wrote that and created that logical architecture is because they're physically, the CV process could be in different physical units. The ASC process is always going to be part of the signal controller, so that's part of your ATC, for example. But the CV applications can reside in 3 different locations, potentially, depending on your vendor. It could be in the same physical unit as the DSRC radio, meaning there might be a unit out there that includes the DSRC antenna, but also contains the CV roads, the CV applications. Or some vendors, some of the signal controller manufacturers are providing, as part of the ATCs, the ability to run some of those CV applications as part of the control unit. It might be a separate card, but the idea is still the same. And then finally, there's the CV roadside process might be in its own separate physical unit. MITS, ITSS, for example, the multimodal ITS system is an example of that. You have a separate DSRC radio antenna. You have a separate Linux box that contains the CV applications, and then you have a separate physical unit, which is the signal controller. So there are 3. That's why we separate the CV roadside process, because physically it might be located in different physical units. Another issue that we had to consider was, if you're familiar with NCCIP, we actually use something called SNMP, Simple Network Management Protocol. And the way SNMP works, there is a component that's considered a manager. So essentially we're asking the question, does the ASC push the SPaT data to the RSU, or does the RSU pull the SPaT data from the ASC? Each of these architectures has its own benefits or issues. Some of them are related to security, part of it's complexity, and it may be determined by the policies of each agency, but we didn't want to define it or make a stand in NCCIP 1202. So we support both both ways. We decided let's let the market decide as it matures, figure out which is better for the manager, which is the better physical architecture, which is preferred. So both of these should be really defined in your specification when you specify how you implement your SPaT, how you implement your SPaT messages. So just to give a little bit more information about 1202 version 3, talking a little bit more detail. So we talked about 4 user needs. One is to configure the RSU interface, so that's managing the ports, managing the watchdog. being able to generate and exchange SPaT data. All the objects related to SPaT in 2735 2016-03, which is the current version, we created objects to address all the mandatory and optional data elements with two exceptions. One is the start time for movement. Even within, remember, because this is an international standard, there's some ambiguity on what is meant by start time. So we did not include that in NCCIP 1202 version 3. And regional extensions we currently don't support because none has been defined for the North American region. We also add some performance requirements, so you can specify how often the SPaT data provided and how quickly is SPaT data provided after the event, meaning something changed, how quickly do we get that information out to the RSU. Generate and exchange SPaT data. There is some issues. One of the big issues that we're trying to that you have to be aware of is the time reference. Your clock on the signal controller may be different from the clock on the roadside unit. The roadside unit should be using, in North America, the global positioning system, but your signal controller may be using a different time source, let's say the Eastern electrical grid, for example. So in NCCIP 1202, the controller provides its timestamps in ticks. We don't say seconds, we use it in ticks, which is equivalent to a tenth of a second. That allows the RSU to resolve the time, figure out, what is the time differences, and then sends out the SPaT data with the correct timestamps. We also, the third user need was to generate a map data. Like I mentioned earlier, we created objects. We needed to make sure, we wanted a way to make sure that SPaT data and the map data is synchronized. If you're providing SPaT data and broadcasting a different map, that's a problem. So we created objects to support all the mandatory and most of the optional data elements for intersection in J2735. And in 1202, we added some objects to provide a check that the current map is being broadcasted, or let's see, what's the right word? A valid map is being broadcasted, but also provide a check that mutually exclusive enabled lanes are not in effect. And finally, we also added objects to support the basic safety, to use basic safety messages and personal safety messages as detector inputs. We essentially create virtual detectors with boundaries that can be defined as a lane or a geofence, and we can use any basic safety message or personal safety message within that boundary and use it as an input into a detector. So, for example, if your signal controller supports 64 detectors, we might be able to use messages or vehicles on that's within a specific boundary as a input into detector number 63, for example. Just some final notes. I mentioned a signal group ID that's used in the map and SPaT messages. In 1202 version 3, we make that equivalent to a channel output number. So if you have an output and channel output number 10, that's equivalent. We made that equivalent to signal group ID number 10. We thought about using the phase numbering, but with the overlaps and pedestrians, we decided that was really difficult. So we made it equivalent to the channel output. 1202 version 3 should be in ballot any day now. Some vendors have started adopting the balloted standard. Note that there is some risk involved. If you try to use 1202 version 3 right away, it's still subject to changes until it gets published. And since we haven't really implemented all 1202 version 3, there's still some lessons learned that we don't have right now. I'm just going to spend 5 more minutes talking about some of the SPaT implementations that currently exist. First is New York City's CV Pilot. They've made the decision to implement the ballot version of 1202 version 3 to provide SPaT data. So they've been working with the ASC working group on implementation issues. Because now J2735 is timestamps, they only send SPaT data to their RSUs when there's a change in the movement status, whether it's the state or the timestamps. Because it's timestamps now, they also send the SPaT data to the Amazon cloud to support pedestrian applications for the visually impaired. In the New York City CV pilot implementation, the RSU will then translate the SPaT data that's received by the signal controller and generate the SPaT messages using the SPaT data to the timestamps in the SPaT data to make the changes so that the SPaT messages provide the correct timestamps. They've taken lots of effort to look at the security as a whole. So their security design for their implementation considers the RSU, the signal controller, and the TMC as a whole system. And because now we're using timestamps, so they don't have to send out the signal controllers doesn't have to send out SPaT data every tenth of a second. It just opens up the channel usage, so there's more wireless channel, more communications time available for other messages. The Tampa CV pilot, they're using Siemens SPaT map application, which is part of Siemens core RSU software. But instead of using the NCCIP 1202 version 3, they're using the SPaT message that's defined in the V2I interface control document that Chris Stanley will talk about a little bit more in detail right after me. So that defines messages or data objects that can get exchanged between the signal controller and the RSU. So it's an alternative method, a second method that can be used. They are using some other functions that's provided by MITS, such as signal priority, but otherwise they're using their own SPaT map application, which takes the SPaT data from the signal controller and resolves it with the map data that's in that's part of their application. And finally, with MITS, their current version of MITS has a roadside processor between the signal controller and the RSC radio, so it's a third physical unit between them. They are using the Patels SPaT message Blob, which consists of NCCIP 1202 version 2 objects with some additional objects that have been defined between the roadside processor and the signal controller. It is based on the 2009 version of the SAE J2735. So so it's not timestamps, it's the time to change. So it has to be sent every tenth of a second. They've started working on, or they're about to start version 2. They haven't made the decision yet, but they're considering using the NCCIP 1202 version 3 object definitions. In summary, the industry still is transitioning to support SPaT. We are still working, the SRC technical committee is still working with different implementations to see what issues we're finding with the SPaT data, including Europe, including North America. But the current options between the RSU and the controller. There's really two options right now. One is the ballot standard of 1202 version 3, which again has its risk. It hasn't been proven yet. But there's also the interface control document that's defined in the V2IHub. My best opinion or suggestion right now is really talk to your vendor provider for the signal controller, see where they are with 1202 version 3 or what they recommend, and work with them. And finally, I have 2 or 3 more slides about resources if you're more interested in finding about the standards, the CV pilot, MITS, or the ISO TS 19091. Thank you very much for your time. Chris?
Thank you. At Saxon Lab, our goal is to develop technologies and tools to improve transportation. And we want that to be more than just research that sits on a shelf and gathers dust, but we actually work to develop solutions that enable engineers to better operate their facilities. I think one of the areas that I've been most impressed with USDOT is their forward-thinking approach with connected vehicles and knowing that operators have existing systems, equipment, and hardware, and that being able to accommodate these new technologies is going to require some translation there and levels of integration. And so for more than 5 years, they've been working on the development of software to manage that with VIHub, software to facilitate the communication between these future connected vehicle hardware and then their existing systems. So what I'd like to do is provide a quick overview of what VIHub is. Why did USDOT develop it? How can it be helpful for operators? Where can information be found? And then what's the roadmap for it and any future functionality? So what is VIHub? Essentially, it's software to simplify the integration by doing this translation between different standards and protocols. It's a modular platform that can use an unlimited number of plugins to add functionality and communication. So it's not unlike a cell phone platform such as Android, where you have that platform and then you can add different apps or plugins that then add functionality or communication. It's essentially a software middleware that runs on an underlying operating system, which is Linux. And then as software, it was purposely designed to be flexible, so it can operate on a variety of roadside equipment to best meet operators' needs. And so that means it could run on the processor of the roadside unit, on a traffic signal controller coprocessor board, or a standalone industrial computer. By using a variety of plugins, you can essentially generate the SAE compliant messages for broadcast. Basic safety message, map, SPaT, traveler information message, position correction, and even future messages as they're developed or needs arrive.
Chris, sorry to interrupt. We're having a little bit of hard time hearing you. Your volume is kind of low. Is it possible for you to speak up a little bit?
Sure. Is that better?
Yeah, much better. Thanks.
Great. So using these plugins, that enables communication with different equipment and systems. And so VIHub has plugins that can connect to the DSRC radio, can communicate with the traffic signal controller, transportation management center, utilize GPS radios for position and for timing. It can also connect with position correction equipment or internet-provided data. At Turner Fairbanks here, we have it connected to a dynamic message sign where it can receive the basic safety messages from vehicles, determine if they're traveling above a speed threshold for a curve, and then automatically generate a warning and send it out NCCIP 1203 to a dynamic message sign to give a visual warning. And then you can connect to other equipment and sensors like road weather, pedestrian, internet, or specialized equipment. And then plugins can also be developed to add functionality and run connected vehicle applications, such as a conflict monitor to make sure that SPaT and map are matching and that it's matching with the traffic signal controller. Multimodal intelligent transportation signal system is actually in process and being added to the VIHub as a variety of plugins to add that functionality. Curve speed warning is one of the applications I mentioned that we have running here, and then we actually use VIHub to conduct hardware in the loop research where we use VISA modeling and we receive basic safety messages from an automated vehicle and vice versa, and so we can both track automated vehicles in VSIM, but then we can also broadcast simulated vehicles and have the automated vehicle respond to those. So what are some of the advantages to this, and why was it developed to help operators? And so some of the first are to reduce the obstacles for integration by being able to provide plugins that enable them to do the translation between both new hardware and their existing in a way that's scalable, efficient, and flexible. VIHub also provides a secure remote access for monitoring and configuration, and so that way to be able to access the equipment or upgrade the firmware or to modify settings, you can do it remotely instead of having to go out into the field. And then it's also been designed to be cross-cutting, both with the existing equipment but also future technologies such as automated vehicles. Documentation has been prepared to enable operators to configure it, to operate it, and also to provide software. I think one of the biggest advantages for operators is going to be that it's an open source platform. In intelligent transportation systems, historically, they tended to be proprietary systems, and so once you make the investment with a particular system and equipment, you kind of get locked or stuck there. But by providing an open source interface, this would enable you to use a variety of different hardware, but also upgrade your system in the future as new technologies come out. So if you developed a plugin and you're currently using one vendor, that plugin would be able to operate on a different piece of equipment running V2I And then it also provides that open source interface for operators to develop their own applications in-house or by third parties. And then this is also something that operators may want to consider when they're going into procurement, is specifying VIHub, particularly for that interface and for the future potential that it would enable them to develop new apps to that interface and maintain that forward and backwards compatibility. And then a couple just very basic examples to bring it down is the generation of the SPaT message. So utilizing the traffic signal controller broadcast messages that were developed according to the 1202 protocol has enabled interoperability. And we actually had a situation that's being referred to as the first example of plug-and-play technology, where the THEA, or Tampa Connected Vehicle Pilot Team, is using Siemens RSUs that were developed to communicate with Econolite controllers. But because Econolite and Siemens both built their RSUs to that same standard, when they came to visit Turner Fairbanks, they were able to plug their RSU into the McCain controller we have here, and it instantly started broadcasting the SPaT and MAP message without requiring any troubleshooting or custom software developments. And so it's been exciting to see how the usage standards actually do simplify and create some consistency. And then I think the other kind of basic example that fits with the SPaT challenge is VIHub has been developed to use USDOT's visual map development tool to generate the intersection geometry. And so by using the tool, VIHub can actually take the output from it and automatically generate and broadcast the DSRC map message. Some of the adoption and locations that VIHub has been used is at Turner Fairbanks and in the Northeast Michigan test bed, at the University of Michigan, Florida's Traffic Engineering Research Laboratory, which actually does the approvals for traffic signal equipment for deployment on roadways in Florida has given it research approval, which was also utilized for the deployment in Osceola County. And then this coming summer, it'll be deployed in Austin, Texas. And then Siemens Roadside Unit actually uses the VIHub software and will utilize the functionality in the Tampa pilot. Currently, VIHub version 3.4 has been posted to the open source application development portal and is available for download. And then I think probably the number one requested functionality I hear from operators is for MITs, and that functionality for preemption and for traffic signal priority for transit and different types of vehicles. And so plugins are in the process of being developed and should be released in June 2018 to enable multimodal traffic signal system functionality and posted to the OSADP. An operational data environment plugin to be able to send data to the cloud will be released in June 2018, and then the final version of the software will be posted in September. Support documentation is in draft form, and it should be released in the next couple months. It would include a guide book, plugins, a development guide, software configuration guide, and administration portals for remote access and configuration, and then a guide to provide plugin. And then as a forward-looking item, FHWA is evaluating additional test plans that may be needed to support procurement of roadside equipment, not limited to VIHub, but based off a lot of the user feedback that we hear is that's something that operators are looking for that can be passed on to the certification boards to help them identify equipment for procurement and to make sure that it provides the functionality promised. And at Saxon Lab, as part of our goal to support operators, we have a connected vehicle support services. And so if anyone does have questions on VIHub or other connected vehicle technologies, particularly in the vehicle to infrastructure area, we're happy to do what we can to support. And with that, I'd like to now transfer the presentation to Faisal Saloon.
Hello, good morning, and actually good afternoon to folks on the east side. And thank you, Chris, and I would like to thank Blaine as well for moderating the session, Nilo for the excellent coordination you have done. And I think before we go and talk about the communications from a connected vehicle perspective, I would like to really thank the National Operations Center of Excellence. I mean, a few years back, who would have imagined that we will have 165 people and we'll be presenting, sitting in our offices and exchanging this great dialogue. So kudos to NOCO. So I know this has been covered, but I just wanted to share this high-level V2I system diagram just to illustrate that the infrastructure systems which are on the left and the vehicle systems which are on the right have to collaborate to support the cooperative safety and mobility applications. So for a meaningful V2I system, the connectivity between the RSUs, or also called RSCs, on the infrastructure side, and the OBU, the onboard unit, also referred as OBE, on the vehicle side of the system is required to enable communications dialogue between the infrastructure and the vehicles. And without such connectivity between RSU and OBUs, the V2I system is essentially incomplete. Therefore, I would focus my presentation more on the right side of this diagram. And from an agency perspective, I would like to say that at least from the agencies that are just deploying the SPaT challenge, it may be beneficial to incorporate in the design and implementation the vehicle subsystem, fundamentally to support testing of their infrastructure deployment, verifying and validating the infrastructure messages. But in a long term, this will also help in preparing for larger fleet deployments in the future so that they can implement applications such as transit and emergency vehicle priority. So from a definitions perspective, OBU is a vehicle-mounted device. The primary function of OBU is to receive and transmit messages to vehicles and infrastructure over the air through the DSRC, the Dedicated Short-Range Communications. So this has been covered earlier, but I would like to draw the difference between OBU and aftermarket safety devices. I think they're one and the same. The only difference is that aftermarket safety devices are not integrated during the vehicle manufacture process, but added after sale. They do have some more software capabilities, and that's something for the agencies to look into when they go through their procurement.
Faisal, could you speak a little bit louder? We have some issues hearing you.
Okay, I will. Thank you. So for the purpose of this presentation, we will use the term OBU. Is it better?
Yes.
Okay, so this plot diagram is just an example of a simple application that provides phase state information to the drivers through the driver vehicle interface, which is on the right. So just to illustrate the function of OBU, which receives and decodes the SPaT and map message over the air. It also receives the vehicle position information from the GPS receiver, or it can be from the vehicle CAN, which is a controller area network. It uses the positioning information to perform lane matching and transmits the phase state and the signal timing information for the match lane to the driver vehicle interface so that the driver gets that information. So this kind of illustrates the various functions that the onboard unit performs in terms of both receiving the data, decoding it, some processing in terms of the lane matching, and then transmitting the information to the vehicle. RSUs and OBUs are very similar in terms of most of the functions, but there are some differences for the agencies to know. Typically, both of them have two radios, but some early versions of the OBU had only one radio. In terms of the specifications, RSU has a standard specification from US DOT, which is 4.1, the latest one, but there is none, or there isn't one for OBU yet. In terms of the FCC licensing, for RSU, the licensing is required, so agency has to go through the licensing process. So there will be a webinar in the future that will be discussing the various aspects of licensing. As far as the OBU is concerned, it is up to the vendor to get the license, so the agency is not responsible for the licensing. Obviously, in terms of installation, RSU goes in the infrastructure side and the OBU on the vehicle side. The power inputs are different. For the RSU, it is power over Ethernet, while for the OBU, it's 12-volt DC power. In terms of the cost of OBU is lower than the RSU, but the cost kind of varies based on the quantity, and that is something that you work with the vendors. Here is just a block diagram of the various subsystems within the OBU, it consists of the SRC services, a GPS receiver, Ethernet port to support graphical user interface, so that, as you can see, it is connected to a tablet for visualization. It has USB ports for data logging, operating system interface. As you see in the box at the bottom, there is an interface to the controller network for the vehicle, and also it can include the Wi-Fi routers. So at the bottom, you also see the connections to the antennas. So the two SRC radio connections and one for the GPS. And there are several manufacturers that supply the DSRC units. I don't have all of them here. This is just to illustrate that there are several vendors out there. What I like to point out is that the OBUs are becoming more and more of plug-and-play installation, so the technology and the installation process is getting better over time. So what is the role of OBU in the SPaT challenge? I think the number one and most important is for the agencies to really know whether the roadside unit is broadcasting the SPaT and map. So in other words, agency may look into having a test vehicle, which is installed with an onboard unit that will support in knowing if the SPaT and map message are actually being broadcasted. It will also provide confirmation if the messages broadcasted from the intersection are transmitted as per J2735 message set, if they're accurate, if the encoding and decoding is proper, the payloads are correct, things like that. Also, it will help the agencies to know if the message is delivered within the required range of the vehicle. We have a direct experience in our testbed where the range for some of the radios was really short, and without having the test vehicle, we wouldn't have known the issue. It was resolved between the vendor and our integrator, but that was really very helpful. Then the verification and validation of messages will also ensure correctness of information transmitted from the infrastructure to the vehicle, and also provide confidence that the OEM implemented applications such as red light violation warning are operating correctly. As a matter of fact, as Blaine shared, there will be a very specific webinar on the topic of verification and validation process. And I encourage you to attend that one. And in the long run, it will help the agencies to learn, and then as they employ their own applications such as EV priority applications, transit priority applications, they will have a good idea of the onboard unit operations. Some of the installation considerations, our experience is mostly on buses and fire trucks, but in general, as compared to RSU, the OBU installation in a vehicle is relatively simple. It will be preferable to provide to the vendor the details such as IP addresses in advance, so that the vendors can properly configure the OBU. This also saves time for the agency, so the vendor doesn't have to spend too much time out in the field. It's good to engage your IT departments. In terms of installation, simple installation includes just connecting the OBU power to the cigarette lighter source, placing the antennas on top for better coverage. The installation on larger vehicles such as fire trucks and buses is more challenging, and in those situations you may have to engage technicians from from the equipment services. They have to provide the power source. For example, when we started installing on the fire trucks, we quickly discovered that the fire trucks don't have a cigarette lighter socket, so you have to create a power source for that. Performance aspects, positioning, accuracy, the SRC range, and the other aspects, that too will be covered in the future seminar that I talked about earlier. But I think it is important for the agencies to know that there are no guidelines available for installing the OBUs in a permanent way in an agency or fleet vehicle. However, we do have some good examples of the installations done by some of the agencies who have been early adopters in installing the OBUs. And I'll start with our experience here. So we have our own incident response team. So our project has been focused, initially we started focusing on emergency response priority. So we equipped some of our React vehicles. Here's an example. On the left, we installed the OBU right under the back seat. And the power source, as I said earlier, was installed by our equipment services. The antennas, the two antennas on the top of the vehicle, these are the shark fin antennas. But that's why I put a question mark there. As you can see, it's sort of permanent, works okay, but I think it's not a finished final product. So there is a need to come up with some guidelines in our industry so that we all have some idea of how to make a more more stable installation of the devices. Here is an example of installing the radio, the OBU, and the antenna on the fire truck. As I said, it gets more challenging. You have a lot of equipment. You have ladder. You have occlusions. So here is our University of Arizona team, and this is a temporary installation of antennas on the fire truck. This is an example from Caltrans. They have been installing OBUs and also RSUs for a long time. They're probably one of the most experienced agencies. They have worked with different models of OBUs. And I don't want to go into the details, but they're using different channels. And also, the Caltrans team has been heavily involved in the development of the software, like our team here with the University of Arizona. So they do use SDK, which is a software development kit. They're not connected to the vehicle CAN. From their experience, they say that the OBUs with two radios work better than with single radio, particularly for applications that utilize multiple DSRC channels. As I said, they have very extensive experience in managing, writing, debugging, and processing scripts on OBU, similar to what our University of Arizona team here. So if you're looking into application development, both of these will be good resources for your developers. They find that SDK is very useful. In addition to the capability of developing and running your own application on the OBU, SDK includes sample applications to help users, developers better understand the OBU platform. Caltrans also suggests to log error status of key processes into files and regularly check the log files and make corrections. Again, this is more like a developer type of application. And finally, from their experience, the new OBUs meet the 2016 version of the standards, and they're becoming more like a black box to the users, which is really good. This is again for some example of Caltrans installation. So here they're installing it in the trunk of the testing vehicle, which is the picture in the middle. They're using the magnet mount antennas on the vehicle roof near the windshield. And as I said earlier, for example, in our case, earlier on we installed the antennas on the driver's side of the bus, and our reception was not that good. And I think what Caltran is saying is that if you install near the windshield, then you get a better signal reception. That picture is on the right side. They get the power to the OBU through a power inverter, which is the picture on the left. We have also started using the power inverters, so that's very helpful. Especially, I think one of the lessons we learned from a demo perspective is in our test vehicles, we keep 2 OBUs, just in case if something goes wrong, and then we have the power inverter, the battery, so we can quickly switch the OBUs. One of the challenges from the earlier version of the OBUs was the reboot, so that's another reason to have a battery source for the power, because it takes like 5 to 10 minutes to reboot OBU. But I think I was talking to some of the vendors, and it seems that this problem has also been resolved. Now the reboot takes about 30 seconds. Here's an example from UDOT, and if I say something wrong, Blaine, help me here. So this is a good example of an operational system where probably one of the first agency or the first agency to have a transit priority system operational on the corridor. They have a nice cabinet in the bus, so it works very well. As you can see, on the very right side is the closer view of the installation in the cabinet. They have a BeagleBone Linux computer, which is running the MITS application and the power supply. From their example, the SRC installation was pretty simple, but the challenges came from the installation of the antenna. They tried several things before getting it to work consistently. The big concern was to avoid penetrating the bus exterior. They found a place in the shroud near the top front of the bus. We can't see it, at least in this picture, unless Blaine points out. So the shroud is a fiberglass, and the placement here has worked very well. I think one of the things that they suggest to keep in mind is that these are external installations, and these vehicles go for a wash on a nightly basis, so they get beat up easily. So you don't pay a lot of attention how to install the antenna so that it's not impacted. So this is a good reference. I just thought I'd share. So the New York pilot, New York City pilot, they had a RFI for ASD, and they wanted to learn what is out there. So there is a link at the bottom which you can use. You can Google it. It's a really good document to take a look if you're interested in OBUs or ASDs. This is one of the examples from the New York City pilot. They again installed the antenna. I think they also had the same challenge as UDOT, and this is the installation right in the middle of the windshield, and that seems to work very well. So if you're looking just from a SPaT challenge perspective, I think a simple installation would work. So just get your OBU, hook up to the cigarette lighter. You can use the magnet antennas, and with the plug-and-play OBUs that are available now, it should be pretty easy and should take like a couple of hours. As I mentioned, if you have the right IP addresses, it should work well. Some of the lessons learned from the installations, So to understand how the full V2I system works and to verify and validate the RSU messages, we do recommend that the agencies include OBUs of systems in their procurement. I would suggest that at least have one or preferably two of the OBUs just for verifying the SPaT challenge messages. I think this will make the SPaT challenge more meaningful. One of the things to consider is the visualization application. Some of vendors provide that so that you can visually see how the messages are flowing and where if the accuracy is correct, if the range is correct, things like that. However, I think there is a need nationally for a generic visualization tool that can support all SPaT deployments. The in-house planning, pre-planning is very helpful. And finally, I would end by saying that there is a need for a procurement spec for OBU. Perhaps it can be done through a CV pilot project. As I said, we'll have a separate webinar focused on performance, validation, and I think with that, thank you for listening to me.
Thank you, Faisal. So I just wanted to quickly remind everyone to register for the next webinar. It will be the second webinar regarding these considerations, and here's the link. So it would cover, like as Blaine and others mentioned, overview of map messages, map creation approaches, and also DSRC licensing and vehicle position correction needs and solutions. The webinar after this one, that is on the design considerations, will present on infrastructure design, intersection and roadside equipment specification design and installations. So at this time, I would like to take the questions and pose it to the presenters here. So with the time we're left, I'll try to do my best to ask as many questions as possible. So let's and to save the time, I'll ask the questions in time, and from the presenters, feel free to jump in or add to the answer. So the first question is, what is the level of accuracy for measuring intersection status, particularly for preemption? Isn't a minute too crude for a measure? And it's asked when Patrick was presenting, so he would be good to answer this. And also, how many bytes would the sum of these data elements would require for both optional and required?
The minute, you're correct, it is too crude. So the SPaT message we expect to be broadcasted roughly about a tenth of a second, every tenth of a second. What I believe I said that might have been confusing is in New York City, they don't plan to provide the SPaT data unless there's a change. So to the RSU. So the RSU is still going to be broadcasting every tenth of a second, but the signal controller in New York City will not provide updated SPaT data unless something changed. So hopefully that answers that question. As for the size of the bytes, I'm embarrassed to say I don't remember. I don't remember what the size of the SPaT message is, what the minimum and the max is. There is a max, but I don't recall off the top of my head what it is. Maybe someone else recalls.
Okay. So let me ask two other questions. So what is the required or envisioned frequency of sending the map message by an RSU? And maybe Blaine could help with this. Also, it was asked, like, what is meant by certified with respect to the V2I hub? certification implies test procedures and an entity that will provide such a compliance assessment and certification assurance. Maybe Chris could help with this one.
So the frequency of the map message is 1 hertz or once per second. I know there's probably some variations on that depending on the application you're running. As we were working with the automakers or group of the automakers through the CAMP organization, and we started to talk about the SPaT challenge, they were very interested in knowing how we were going to verify that the messages we send meet their needs from the automaker standpoint. And the outgrowth of that conversation was a SPaT challenge verification document, which they prepared and you can download from the SPaT challenge site. And in there, they've specified that the map message be transmitted once a second, or 1 hertz.
Can you repeat the question, Nilu?
Yes. So what is meant by certified with respect to V2I Certification implies test procedures and an entity that will provide such a compliance assessment and certification assurance.
Yes, so that was more of a forward-looking statement, and as in the DOT is looking into what future needs there are for roadside equipment. And so would there be parts of VIHub or certain functionality? Would it be data elements out of the traffic signal controller, but they're looking at other elements where test plans would need to be developed and then handed off to industry and one of the certification boards to be able to utilize. And so it is the goal that to do an assessment and then be able to provide something that would help deployers and people in procurement to identify and use for certification.
Thanks. While I have you on, there's another question on V2I. So the question is V2I supported on Trafficware hardware?
I'm not aware that they've adopted it. It's available for them to. I think there was also another question about which hardware or equipment is most used, at least in regard for the VIHub. It works with the Cobalt controller. We have it with the Econolite ASC3 and the firmware 2.58 or greater, and then we also have it with the McCain ATC rack mount. And then I know there's a Siemens controller that has adopted those NCCIP 1202 data objects, and then most RSUs would be able to work with it that are compliant with the 4.1 standard of the message forward.
Thanks, Chris. So we have a few questions about interoperability. So I'll read them out loud. One question is, do an ASC and RSU need to support both approaches? There might be an issue with interoperability if it is not carefully specified in RFP. And the other question is the ARADA system RSU with Cobalt controller the most common combination used for pilots nationwide? And another question that's relevant is that is there somewhere where we can find which controller model would best be compatible with which RSU model or vendor?
This is Patrick. I'll tackle the first one. Yeah, in terms of interoperability, there are, unfortunately, right now, multiple approaches. So, for example, I talked about which one does the RSU push, the ASC push the data to the RSU, or does the RSU pull the data from the controller? And yes, that's an interoperability issue. So you need to include in your specification how do you want that data exchange to happen. Should it be a push? Should it be a pull? If you want to support both approaches, that's possible, but chances are your agency has to decide which way works best for you and to support that one approach. So your specification should make clear, how is it that you want to implement exchange the data. As for the errata and the COBOL, I don't know if we've done a survey of which controllers work with which RSUs, but so I don't know which is the most popular combination right now. I'm sorry, I forgot the third question. I don't know, Blaine, if you want to add to that, the one I just answered.
Yeah, this is Blaine. Let me jump in there a little bit. So everyone's using different equipment, and there are a number of different signal controllers we all use, and there are a half a dozen different vendors of DSRC equipment, or a few more than that now. And so everybody's using different combinations. Errata was purchased by Lear, and so the old Errata equipment, you may still be able to buy some, but I'm not sure they're supporting it yet, just to get specific about that question. Some of the controller vendors have started to make marketing arrangements, if you will, with some of the DSRC vendors. So the thing you should do is talk to your controller vendor and see if they have worked out some arrangements with certain DSRC vendors for their equipment to work together. And that's probably the best step. There's a broad number of coalitions or of combinations of equipment out there. We've got both Intolite and Econolite controllers, and we have DSRC units from 4 different vendors on our system that we've made work. And so there's a broad realm of possibilities.
Did I skip a question? Was there one more question? I apologize. I think there were 3.
I think I got both the second and third one, yeah.
Great.
Actually, it was like along those same lines. The third one was that does somebody have the information on who is using which controller model with which RSU? So similar to what you answered.
We covered that.
Yeah. Let me ask another question. So is there a handshake between the RSU and the SPaT controller when the information is being sent? And the second question is, how do we know that the RSU is sending SPaT? Is the RSU smart enough to detect its own fault and transmission?
Unfortunately, the handshake is also implementation specific. There are some vendors that believe that, hey, I'm going to send the SPaT data to the RSU. If the RSU receives it in time, terrific. If it doesn't, well, in a tenth of a second, maybe, I might resend it also. So in that case, as long as I'm broadcasting it, or UTP, I'm only interested in the latest one. I don't really care if you receive it or not, because I might send another one in the 10th second. Other vendors may say, no, I want the handshake. I want to confirm back, provide back to you that, yes, I did receive it, so you can stop. So unfortunately, it could go both ways. It's how you implement it.
So I think that's the purpose of what I was suggesting is having a test vehicle that the agencies can have a OBU installed with a visualization tool, so they can see what messages are coming across on the vehicle side. I mean, that's the whole goal, is to transmit the message to the vehicle side. So there is a value in having agency having a test vehicle and getting the messages.
I'll add a bit to that one as well, where most of the RSUs do have some kind of log files and tracking of their operations to say whether they're broadcasting or not, and I know that VIHub does as well. But that is one of the big questions or challenges is, okay, I got it plugged in and it's broadcasting, but you can't really see that. You could get a packet sniffer, which is a bit of work, and see a bunch of ones and zeros and to see how it's going. But one thing that we're looking into is being able to provide a test device that has a visual display. We have one that we use here that receives the messages, the map and the SPaT, and then it visually displays it on a tablet so you can see the intersection, the lanes, and then you can see the signal phase and timing in real time and watch it change on the tablet along with the traffic signals. So that's one item we're hearing increased requests for, because it's very visual and very quick and easy to figure out, hey, is this unit working or not? So I guess if that's something people are interested in, if they, in the information I provided, it provides a support services and a semantic side. If you guys put in requests for this, then that means we can move it to the top of our list of priorities.
Thanks, Chris. So 2 questions about the SAE J2735. First one is, have you considered extensibility in regard to SAE J2735, for example, integrating speed limits per intersection and per line? And the second question is, do all RSUs conform with NCCIP and SAE J2735 standard?
This is Patrick. I'll answer that one. There is extensibility built into the to the J2735. That's what's called regional extension. So a region such as North America or Europe, or maybe even the state, for example, can add their own extensions. And Europe, for example, has added some extensions to their implementation of SPaT. The speed limits, I believe, are in there. They're part of the map message. So you can include the regulatory speed limit as part of the map message. I forget how we would handle variable speed limits. I need to check that. But for a posted speed limit, that would be part of the map message. Right now, the RSUs should conform to the J2735. You can look at the RSU specification, but what does that really mean? So if you're providing SPaT data, SPaT message, for example, yes, then you should conform to the J2735 SPaT message. If you're only providing map, then you should conform to the J2730 map messages. So it could mean different things. If you want to read the basic safety message, then you want to be able to read the J27 basic safety messages. As for NCCIP 1202, it's still in ballot, so there are no RSUs that conform to the version 3 of NCCIP 1202, but if you support the V2I hub, for example, you support some of the objects that are defined in NCCIP 1202 version 2. So I kind of answered it. I kind of didn't, but hopefully I did answer it.
I'll see if I can add to that. So in regard to the RSUs, we're evaluating 3 of them for compliance with the 4.1 specification, and should within the next month have that testing finished and a document released for people to see how compliant they are with that specification. And then in regard to the Siemens RSU, I think they've incorporated, I don't think it's a custom model that is using VIHub. I think it's part of their integration. VIHub's still in development, so I'm not sure how much functionality that they've adopted, but looking at some of their instructions that go with it, they reference the VIHub, and so I don't want to speak overly for them, but they've been pretty integrated with it throughout VIHub's history.
Let me add one more detail. We've actually started working on an NCCIP standard for RSUs. The NCCIP, it's going to be called NCCIP 1218, is going to be a standard so that we can manage and interface, monitor roadside unit. That work is just starting. We're still in the concept of operations phase. So hopefully in about a year from now, we may have a initial draft. Maybe about 2 years from now, hopefully less, we may have a standard for managing and monitoring a roadside unit.
Thanks for those answers. So somebody asked, could you elaborate on the procurement challenges for equipment and the need to a pilot procurement? Would that go through SCP 14?
I'm not sure what SCP 14 is, unfortunately.
The person
So this is Blaine. I'm not either. We talked about procurement on the previous webinar, so the questioner should probably go back and listen to the latter part of that webinar. We talked about that a little more. But you saw some things in today's webinar that are important. When you go to purchase DSRC equipment, the RSUs should follow the 4.1 specification for RSUs. You probably should spend some time thinking about what applications you might want to run beyond the SPaT challenge on that corridor, and make sure that you specify that those message sets are supported. Some of our colleagues are finding that as they procure RSUs, they're finding it useful to put in their procurement document that after they make some preliminary selections, they have an opportunity to get their hands on some of the devices that are being offered and test them in the field to make sure they really meet their needs and their specifications and their document. And so that's not a bad idea. Most of us are used to doing that with other kinds of ITS equipment. So those are some off-the-cuff ideas about procurement. And then, of course, you have to follow the procurement rules of your own agency, whatever those might be.
Thanks, Blaine, for that. And I think there's another question about security concerns. So maybe we touched briefly on this in the previous webinar, but I'll just read the question. What security concern implementations are supported by RSU and controllers?
Nobody wants that one, do they?
Yeah, I'm trying to figure out the best way to answer it. The CV pilots are using the Security Credential Management System, so that's SCMS. Unfortunately, that version is only available to the CV pilots or if it's federally funded. The other option is you can do something similar, get certificates, but you'd have to do other private vendors, but you'd have to pay for it. The New York City CV pilot is looking at it a little differently, so they've been trying to look at security as a whole, meaning the RSU, the signal controllers, and the traffic management center. So they've been looking at, I forget what the acronym stands for, but it's TLS 1.2 to try and support to provide security for not only the information at the RSU, but also at the controller from the TMC. So it's another area that's unfortunately still ongoing. I would reach out to New York City and maybe any of the CV pilots and ask them what they're doing for security in addition to the SCMS. Blake or Chris or Faisal?
Yeah, I would just like to add, I think they're very close to that. I think it's a matter of like 6 months or so. I think that's my understanding, that they will have a good feedback for us on the security side. And this is a really important question. I mean, being an agency, it's a matter of concern, and we all are. So we're looking, you're right, we're looking to the pilots, and New York would be a good example for all of us.
And I'd just add that they are looking at both elements. One is the certificates, the signing of the messages, and then also the entire system. And I know we're about to procure some equipment and test it for end-to-end security of your operation system from your TMC to your traffic signal controllers and big level threat detection and intrusion and a variety of different potential risks.
So from a procurement perspective, I think it'll be good to have some kind of a standard language that we get from the pilots for incorporating in our RFPs.
Thanks. So there were two questions more with the details on the parts that Patrick presented. So the first question is if a left turn is prohibited during the rush hour, can it be defined as a through using a different lane designation? And the other is about NCCIP. So do CV objects in NCCIP only reference the objects in J2735 and does not repeat them?
For the left turn in the map message, you would be able to indicate that there's a movement for a left turn, and there would be a movement for through, for example. But in the SPaT message, you would only indicate provide information about the through movement. The left turn, the information about the left turn just would not appear in the SPaT message, indicating kind of by default that it's not supported. The 1202 objects reference the J2735 objects. We can't use them directly because the structure of the standards are different. So in NCCIP, we use tables and rows. They don't have such a structure in the J2735, so we really reference those, the SAE J2735 objects.
Thanks. So one question here is somebody asked, who is and why New York sending their SPaT data for use in the app that assists the visually impaired? Can you share more information on that? And do you know anybody who we can contact from New York?
I would, yeah. Originally, they were when the New York City CV pilot submitted their proposal. Their original plan was to provide through the SRC the SPaT or information to smartphones for visually impaired pedestrians using the SRC. They had issues with that, so they're doing it through Amazon Cloud right now. The person to contact would be Mohammed Talis, and if you look at the he's from New York City DOT. If you look at the CV pilot's website, I'm sure his contact information would be there.
Thank you, and I think that would be the last question. We really respect your time and appreciate you going over the dedicated time. We had many good questions, so I just went over a few minutes to ask those from our panelists here. So I'll just take a moment to thank everyone for attending today's webinar and thank especially our panelists who shared some good information with us today. Again,